Here we are going to discuss the binary and octal. The theorem is, if base r1 is the integer power of other base r2, that is r1 is equal to r2 to the power d. For example, 8 equals 2 to the power 3. Every group of d digits in a r2, for example 3 digits, is equivalent to 1 digit in the r1 base. Note, this theorem is used to convert binary numbers to octal and hexadecimal, or the other way around. Here from the theorem, assume that r1 is equal to 8 base 8 octal and r2 is equal to 2 base 2 binary. From the theorem above, r1 is equal to r2 to the power d, 8 equals 2 to the power 3. So 3 digits in base 2 binary is equivalent to 1 digit in base 8, which is octal. From the stated theorem, the following is binary octal conversion table. You can simply see the table here. There are the system of numbers, and in matrix form, the binary and the octal 001, 001, 010, 011, 100, 101, 110, 111, same 000 in octal 0, 001 in octal 1, 010 in octal 2, 011 in octal 3, 100 in octal 4, 101 in octal 5, 110 in octal 6, and 111 in octal 7. So in a computer system, the conversion from binary to octal or otherwise is based on the conversion table above. The digits in base 2 binary is equivalent to 1 digit in base 8, which is octal, and here the convert these binary numbers into octal numbers 0010 11112. The total number of bits are 8 here. You can count 2, 2, 2 and 2, 8 bits, and same 1111 01 002, 8 bits. So refer to binary octal conversion table 000 101 111. Here 0, 5 and 7, so 57 to the base 8 in octal system, and refer to the binary octal conversion table 011 110 100, so 364 here, 364 to the base 8. There are some points to be noted. The same method employed in binary octal conversion is used once again. Assume that r1 is equal to 16 in hexadecimal, r2 is equal to 2 in binary. From the theorem, 16 is equal to 2 to the power 4, hence 4 digits in a binary number is equivalent to 1 digit in the hexadecimal number system and otherwise. The following is the binary hexadecimal conversion table. In binary, 0000 0001 0010 0011 1000 0000 0101 0110 0111 1000 1001 1010 1011 1100 1101 1110 and 1111. So here in hexadecimal 0 1 2 3 4 5 6 7 8 9 A B C D E F. Here once again, A is for 10 and B is for 11 and C is for 12, D is for 13, E is for 14, and F is for 15. Because we are taking 0 to 15 total number of digits for the hexadecimal less than 16, convert the following binary numbers into the hexadecimal numbers. So here is the binary number 0010 1111 to the base 2. Refer to the binary hexadecimal conversion table above 0010 and 1112. Here this is the conversion. So 2F16 here is the final conversion.